Welcome back. So we are in the next lecture in power electronics. In the previous module, we discussed on uncontrolled rectifiers. In this particular lecture, we will focus on the controlled rectifiers, and the load that we will take is basically the resistive load and the inductive load. The supply is basically the single phase AC supply, and we will do the analysis of the different rectifier configurations when the load is basically resistive and inductive load. So this is the first lecture of this module where we are discussing on the control rectifiers. Let us see the outline. So first we will introduce about the control rectifiers and see how it is different from the uncontrolled rectifier. We'll classify the single phase control rectifier among different categories which we will cover over the lectures. The half controlled converters using the resistive load, we will do the analysis and performance characteristic we will see. The same we will do with the RL load, and then we will conclude with the summary and the applications. So the introduction to control rectifiers, we have studied the uncontrolled rectifier, and the limitations of the uncontrolled rectifier is the average output voltage is constant for a given load and fixed input voltage. So we cannot change the output voltage for a given load condition, and it is fixed. Variable output will require additional components like auto transformer, the variac, and the tap changing transformer. So the disadvantage of these traditional methods of increasing the output voltage, or rather the variable output voltage, is using the different devices which make the system to be large, size is increased, and the weight is heavy. Cost obviously will increase with the equipment, and the complexity will also increase, and this will be limited over a particular control range. So basically, in order to solve this problem, we will focus on the control rectifier, which is a solution, and it provides the better alternative or the solution with the compact design and the precise control. So uncontrolled rectifier can be replaced with the controlled rectifiers. The control rectifiers are heavily used in industrial applications in terms of the electric traction system, the steel rolling machines, the paper mills, textile mills, magnet power supply, and electromechanical devices. So these are the various industrial sectors where the control rectifiers are basically used. Now the power semiconductor devices. So we have introduced about the power semiconductor devices where we talk about the power diode, and we have seen the on characteristic and the off characteristic. So this is basically when the forward biased voltage and the input voltage is greater than the cutoff voltage, and the diode will be on, and the diode, when it is reversed bias, then it will be off. And diode is also the unidirectional power semiconductor device, whereas the silicon control rectifier SCR will be on only when the forward biasing is there and we need to trigger the pulse which is applied. In the off condition, we apply the reverse biased or the commutation voltage. So this difference between the power diode and the power silicon control rectifiers we have discussed in very detail. The key characteristic in this case is basically the devices are turned on and off sequentially and repetitively to control the power flow. So whenever with the use of the gate pulse, we can basically control the signal, and we can turn on and off whenever we required as per the commutation principle. So again, when we talk about the commutation method, especially for the silicon control rectifiers, then there are two important categories that we have seen. Natural commutation and forced commutation. In the natural commutation, which is basically the line commutations, here the SCR will be turned off when the applied AC voltage will become 0. This is commonly used in basically the control rectifier circuit. It is simple and also reliable. But the forced commutation is the artificial commutation where we use basically specially designed circuit, and this will apply the reverse voltage across the SCRs, and it will force the SCR to turn off. So the classification overview of these rectifiers, when diodes are basically replaced with the SCRs, the rectifiers are known as the uncontrolled rectifiers. So when we were using the diodes, that time we were having the uncontrolled, and now the diodes will be replaced with the SCRs, and hence we will be getting the controlled output voltage, which is obtained by controlling the delay angle alpha. The variable voltage which is available at the output terminal will be used for different industrial applications. So if we classify in terms of the pulses, then we can have either single phase half wave, which is one pulse control converter, or single phase full wave, which is two pulse control converter. It means that if we rectify both the positive and the negative half of the AC input supply, then it is basically the full wave, or otherwise two pulses. If we rectify only the one of the pulses, that is the positive half, then it is basically half wave control converter. This all discussions we have detailed in the uncontrolled converter using the diodes, but now we are going to focus on the controlled version of these rectifiers. So single phase controlled converters or the rectifiers can be half wave, one pulse, and it can be without freewheeling diode or with freewheeling diode. In this particular lecture, we will not use any freewheeling diode, and the next lecture we will see how the freewheeling diode plays an important role in especially the RL load conditions. So whenever you have the RL load conditions, in that case the freewheeling diode plays a very important role. Similarly in the diode rectifiers also. So in the full wave, which is the two pulse converter, again we will see about the full converter or the semi converter. Full converter where we will not use any freewheeling diode, and the semi converter we will be using with freewheeling diode. So many applications and configurations are there in terms of these control converters. So we will see one by one about all these configurations. So let us begin with the first type of the load, that is the R load. So the single phase AC source is being given to the rectification principle. So AC will be converted to DC. Now the input is AC, which is single phase, and the output that we will be getting at the resistive load is the DC. Now instead of using the diode, we are now using the thyristor. So this is the thyristor or the silicon control rectifier which we are using instead of the diode. So it is basically known as the controlled rectifier, and it is a control switch. How we are controlling? We are controlling with the respect of the gate. So there is a gate signal which we can apply, and we can control the output voltage and the output current. Now in this configuration, we will take the resistive load, and then we will discuss the RL load, and with freewheeling diode, without freewheeling diode, all those things we will be discussing. So in the single phase half control converter, the input voltage is AC, so that can be written in the form of root 2 V sin omega t, where V is basically the maximum voltage, and the output that we are getting V naught and I naught, these are the basically the DC voltage, which are the average voltage. So thyristor will be conducted only when the anode is basically positive with respect to cathode. So this is the basic principle of the SCR, that anode has to be positive with respect to cathode, then only the conduction will begin. And we have to apply a gate pulse also, which is positive. Otherwise what will happen, that the SCR will be operating in the forward blocking state. So in order to trigger this thyristor, we basically require two important condition, that anode voltage should be positive with respect to cathode, and the gate pulse we have to apply. Now the operating principle of this R load in the positive half cycle and the negative half cycle, that we will see. So in the positive half cycle, the thyristor T1 will be forward biased, and we are basically firing the thyristor at omega t is equal to alpha. So there will be conduction process will begin, and it will continue up to pi, omega t equal to pi. That is the first positive half cycle. In the negative half cycle, the thyristor T1 is now reverse biased. So it is turned off at omega t equal to pi. And the commutation that we are taking is basically the natural commutation, and the load current will become zero because you don't have any supply now, which is commutated. Thyristor is commutated. So control mechanism, the average output voltage is basically controlled by varying this firing angle alpha. So the gate supply that we are giving to control the firing angle alpha will be basically controlling the output voltage. So hence it is known as the control rectifier. Now these are basically the voltage and the current waveforms for the single phase half controlled converter with the resistive load. So you can see the supply voltage, it is basically AC. So we are having both positive and negative half cycle of the AC wave. We are applying the gate pulse at a control angle of alpha, so this is the delay angle or the firing angle, we will be getting the V0 and I0, which are the basically the voltage and the current, the DC voltage at the resistive terminal. So the load is basically resistive in nature. So here you can see that conduction process will take place from alpha to pi in the positive half cycle, and the negative half cycle there will be no pulse. Similarly, again the signal will begin from 2 pi plus alpha to 3 pi plus 3 pi. So both the positive half cycle of the AC input will be rectified, but the negative half cycle will not be rectified. So hence it is known as half controlled converter. Now, if you see the thyristor voltage, so thyristor will be turned on at basically the alpha where the firing angle is given, and it will be full reverse voltage will be applied from pi to 2 pi. So thyristor will has to sustain those reverse biased voltage. Now, if we talk about the key characteristic of this resistive load, the waveform properties, so average output waveform will be same as the output current waveform, and there will be zero phase difference because the load is resistive in nature. So the DC output voltage will always be positive and the current will always be positive in this case. This type of thyristor operation for half controlled is operating in the first quadrant only, and we are known to have the half wave semi converter. So this is basically a semi converter with a half wave operation. If we do the mathematical analysis of this resistive load, the output voltage that we get V0 is equal to root 2 V sin omega t for omega t in the alpha to pi value, and the voltage will be 0 when omega t is greater than the value of in the alpha to pi or omega pi to 2 pi. So there the V0 will be 0. And if this is the output voltage expression, and this is the average output voltage, which is the DC, which we are getting at the load. So root 2 V by pi 1 plus cos alpha, this is what we get at the resistive load, which is the DC voltage, and we can substitute the value of alpha to the extreme cases to get the maximum and the minimum value of this voltage. So alpha will be 0, then you will get the maximum DC voltage. Alpha becoming pi, we will get the minimum DC voltage, that is equal to 0, means you do not have any DC voltage. Now, if we do the RMS output voltage, which we are finding, so RMS voltage can be found out as a root mean square of the AC voltage. So this is what the formula we can use it to find the RMS output voltage, V under root of 1 by 2 pi, pi minus alpha sin 2 alpha by 2. So here the alpha is basically that firing angle, which is basically controlling the total output voltage or the DC voltage. So it is a controlled rectifier. The DC voltage can be obtained as the DC voltage by resistor is the DC current. So IDC we can obtain it, and we can substitute the voltage formula here to find the current. Similarly, the RMS current, when we need to estimate, we can estimate from the RMS voltage. So VRMS by the resistive load will be the RMS current. If we need to find the power, power is basically the product of voltage into current. So this is what we have in the DC. So we can get the formula for the power. When we talk about the AC power, this is product of RMS voltage into RMS current. So given the condition whether we need to find the DC voltage or we need to find the AC voltage, we can use these expressions, whether DC voltage into DC current will give you the DC power, and the RMS voltage into RMS current will give you the AC power. Other factors that we need to estimate is basically the form factor, so which is the RMS current by the DC current. So we can use this formula, which we got it from the previous expressions of the RMS current and the DC current. The ripple factor is under root of form factor square minus 1. So form factor we have estimated, we can substitute here and we can get the ripple factor. Transformer utilization factor is basically the ratio of the DC power by the volt ampere rating of the transformer, so that we can get it by this formula. So we are using the transformer to step down, because again the transformer is basically used, we have discussed in case of uncontrolled rectifier. So whatever the voltage we are giving it, this may be a high voltage, and we need to have the voltage at the step down here to get a certain voltage, and after that the rectification principle will begin. So transformer utilization factor is one of the consideration that we can estimate. If we do the firing angle analysis, so what are the key operating points? So the maximum average output we get at 50% condition, where the maximum average output voltage at alpha will be 0. For 50% of the maximum, 1 plus cos alpha will be equal to 1. So at alpha equal to 90 degree, we will be getting the maximum average output voltage. So the control range here, the DC output voltage will vary from the value 2 root 2 V by pi to 0 when we control the firing angle from 0 to pi. So in this case, we can vary the voltage from one level to another level when we control the firing angle, and hence it is known as controlled converters. Now instead of using the resistive load, we are using the RL load condition. So here you can see, apart from R, we have L also, which is the inductive load. So here we again, the input that we give is basically the same, which is the AC voltage source, and thyristor will be used, which is basically the control switch, and the load that we are using is a combination of resistive and inductive in nature. So what makes the key difference? The operation will differ significantly from the pure resistive load due to the inductive effect. So when we have the resistive load, the voltage and the current are in phase with each other in case of resistive, but in inductive, because of the phase difference, it will play an important significant difference. So what happened at the positive half cycle? Let us do the analysis. Again, the thyristor will be forward biased. We will apply the gate pulse at omega t equal to alpha. Thyristor will be turned on, and the input voltage will be applying across the load. Now the load is basically the combination of RL. Now the inductive load, there is an effect, which is the current will increase gradually from 0 and it will reach the maximum, then it will decrease. So current continues to flow even the input voltage reverses. So when the input voltage is not present or reverses, there should not be any output, but because of the presence of the inductor, there will be certain output voltage also here. So conduction period, if we talk about, the thyristor will start conducting at the firing angle alpha, which is omega t, and thyristor will be turned on at omega t equal to beta, which is extinction angle. So this is off condition, and the total conduction period will be beta minus alpha. So this is the conduction angle. Important note here is basically that thyristor will remain the on condition despite the reverse bias condition due to the inductive current continuation. So this is what we have to note, the key difference between the R condition and the RL load condition, that even the thyristor is given the reverse bias, the current is not becoming 0. So let us see this from this voltage and the current waveform. So here you can see the input voltage, which is basically the AC voltage having positive and negative. We are applying the gate pulse at a delay angle of alpha. Now if you see the output voltage at a pi value, when it was a resistive load, the voltage was becoming 0, but it is not becoming 0 due to the presence of the inductive load, and the extinction is basically taking place at beta. Similarly, the current, if you see, till beta you have the current, and thyristor voltage, which is turn on condition and turn off condition, has now delayed by beta. So this is the effect of the inductor, that due to the presence of the inductor, this unwanted condition has occurred, that at pi we need to turn off the output voltage, but because of the presence of the energy at the inductor, it will not be turned off, and the conduction angle will be little bit more as compared to the resistive load. So if you do the voltage expressions, that is V naught equal to Vm sin omega t for omega t alpha to beta, beta being the total conduction angle, V naught will be 0 for omega t from 0 to alpha and beta to 2 pi. So there will be two operating modes now in this case. One is the rectification mode, when the omega t is alpha to pi, power will be flowing from supply to the load condition, and the inversion mode, when omega t is pi by beta, power will be flowing from the load to the supply. So the energy which is present in the inductor will be reverse its direction, and it will start flowing from the load to the supply end. So if we do the analysis, mathematical analysis, when the thyristor is on, we can write down the equation Vm sin omega t is equal to the voltage of the inductor, which is L di by dt, and the voltage of the resistor, which is R into I naught. So under the steady state condition, the solution to this is Vm by Z sine of omega t minus phi, where Z is the total impedance because of the resistive inductive load. And the transient condition, we get A e to the power minus R by L into T. So the time constant is basically L by R. And the impedance we can calculate under root of R square plus omega square, and the phase angle, which is omega L by R. So these are basically the normal transient and the steady state equations when the RL load is there with respect to the AC conditions. The total output current that we get I naught with a function of time t can be estimated using these expressions, which is involving the value of both alpha as well as phi. So here the boundary condition, if we check that at the extinction when the current is 0, omega t is equal to beta. So it is at beta when the current is becoming 0, it should be pi if the load is resistive in nature. So we can use the equation to determine the extinction angle beta by equating this expression. Sin beta minus phi is equal to the expression sin alpha minus pi e to the power minus R by omega L beta minus alpha. So if we equate this, we can estimate what is the beta at which this extinction has taken place. Again, the average output voltage, if you want to estimate, which will be used by this formula Vm by 2 pi cos alpha minus cos beta, maximum value will be beta at equal to pi and decrease as beta will increase. So RMS voltage, if you want to calculate, then we can calculate by these expressions, which is basically the depending upon the values of alpha, beta and the maximum value of the voltage. Similar to the previous one, we can calculate the form factor, which is RMS voltage by average voltage. And this is the simplified expression that we will get. Form factor will indicate the shape of the output waveform, what nature we are basically getting, because it is a sinusoidal wave. And the transient current which is present due to the inductive effect, we can calculate by these expressions. So if we talk about the special cases, no transient current is possible only when the sin alpha minus pi is equal to 0, and maximum transient can take place when sin alpha minus pi is plus minus 1. So these conditions are important when we talk about the circuit design and the protection when we are designing the RL network. In that case, we need to have the knowledge of the maximum and the minimum transient current conditions. As in RL load, we have the first quadrant operation. In the resistive load, in the RL load, we have two quadrant operation. So single phase half wave controlled rectifier with RL load will operate in the first quadrant when it is in the rectification mode, in the fourth quadrant when it is in the inversion mode. So RL load, we have only one quadrant, which is the rectification, but in RL we have two quadrant operation. One is the rectification and other one is the inversion. So key features is average output voltage can be positive or negative. If you remember, the R load was having only positive output voltage, but now we are having negative also. And it depends upon the firing angle alpha, and it is a bidirectional power flow capability which makes it to be full converter. So instead of half converter, we are getting full converter because bidirectional power flow capability is there. Let us summarize what we have discussed for the single phase half wave controlled rectifier with R load, which is simpler in analysis. Current will flow as the voltage and it is the first quadrant operation. Whereas in RL load, it is complex due to the presence of the inductance. You will basically have the two quadrant operation with rectification and the inversion. There will be bidirectional power flow. Power will be flowing from source to load as well as load to source. And the firing angle alpha will control the output. Extinction angle beta will depend upon what type of load you are putting, and the conduction angle beta minus alpha will determine the power transfer flow. So application wise, if we talk about, then we use in power supply, energy storage and motor control. All are these industrial applications for talking about the DC power supplies, the variable voltage source, battery charging, energy recovery system, DC motor control, speed regulations. Everywhere we can think of this single phase RL load condition converter operation. So these advantages, it has a precise voltage control, high efficiency, compact design, and cost effective solutions. So we have discussed in this particular lecture about the single phase rectifier with two important load conditions, R and RL. And in the inductive load, we have found out that yes, the current is not becoming zero because of the energy which is present in the inductor. So now in the next lecture, we will see what is the role of the freewheeling diode in such cases. And also we will be taking another important load conditions, that is RLE load. So this is the motor operation, how the EMF plays an important role in the load conditions. So RLE load is one of the important load conditions that we will see with the help of these rectifiers. We'll do the analysis performance characteristic. Thank you for now.